Hello guys, so let's continue our derivation on equilibrium equations. But this time let's try to consider the rotational aspect of equilibrium, which is the moment equilibrium equation. So this may be understood easily by referring to the example I gave you about special tensors, wherein the moment of a force about a point on the three-dimensional space was derived considering a special tensor known as the permutation tensor. So this is the epsilon ijk tensor. So take note that in the formulation from example 1.4.2, the moment is simply defined as the force multiplied by the distance. Okay, wherein the forces we are referring here to are the FIs, no, and the distances are the YJs, such that our resulting equations were actually in the form F2 Y3, okay, minus F3 Y2 E1. Okay, so this is the first uh, a moment expression as directed to the E1 unit direction, and the second one is the F3Y1 minus F1 Y3 E2. Okay, so and the third one is the F2 Y3 minus the F3 Y2 E3. Okay, so in this format, this is actually equivalent to the epsilon ijk. So this is equivalent to epsilon ijk of your Fi Yj epsilon k. So take a look at the format. No, this is a coming from the permutation tensor, and it is a determinant operation upon which these three quantities, vectorial quantities that were derived from. So without putting into too much detail, the expression of the moment of a vector, attraction vector, and the body force as represented here in these expressions. So this is in terms of the traction force or the traction vector, this which has a sigma IRJ, this is the moment arm, and we have also here the body force, which is the rho Fi, and this is actually the innate body moment or the inherent body moment Wi. So this is the um, given uh, internal moment inside a particle or inside the body upon which your domain or the region R is being represented on. Okay, so so take a look at the format. It's a simple an epsilon ijk, F becomes sigma, Y becomes R, and then epsilon EK direction was simply ignored because this is a, uh, a more compact expression, but there is an implication these are directed at the direction k, since this is an epsilon ijk. So actually we don't need to write down the ek here to make it more compact, because these are just what the k here actually implies that there's a direction ek present within this expression, and so is true with this. And since this is a body moment, on which in which the direction may be defined differently from one body to the other. So we do not consider here a directional unit vector. Okay. So equation 2.6.3 is actually uh, the general equation that defines your moment equilibrium condition. But again, if you are looking into the dimension of your boundary here and the domain dV there, of course, there's also a domain dV here. There's an inconsistency in this summation. So what we are going to do is again use the Gauss divergence theorem to make such inconsistency uh, to correct such inconsistency rather. And using the Gauss divergence theorem, uh, but first we need to change the traction variable into a tensor variable by using the vector tensor relationship. So we know that sigma I is simply equivalent to nj sigma ji. Okay, so this is simply a sigma I equivalent to nj sigma ji, or by using a different index here in terms of j, I use an m here to avoid inconsistency on the existing j that describes your moment arm relationship. So I cannot use a sigma ji. Rather, I have to use a different index. So I use a sigma mi dot nm. And notice that I now transpose a vector notation into a tensor relationship upon which this particular uh, uh, tensorial vector product will lead me to the opportunity of using the divergence theorem so that I may be able to change the boundary, okay, the boundary variable into a domain variable, or simply the surface variable into the volume variable. Okay, so that's the objective of trying to look at the procedure and how to appreciate more your general moment equilibrium equation into a more specific moment equilibrium equation. And if I now consider a change in the quantity in terms of a surface quantity to a volume quantity, I have to consider a derivative. And since these RJs and MIs are functions of position, they are both spatial dimensions. Therefore, this is simply a derivative of a product, a partial derivative of a product with respect to DRM. So I will be using now the sum of the partial derivatives. No, so the derivative of a product is simply the first multiplied by the derivative of the second plus the second multiplied by the derivative of the first. Okay, so we have two resulting derivatives here, derivative expression, which will be this one here. Okay, so epsilon ijk ddm. Okay, so this is not ddm but drm. Okay, so this is an r representing the vector of position, or the position vector, which is a function of your coordinate axis xyz, or x1 x2 x3, or r1 r2 r3, whatever variable I want to use. So this is now a product derivative, so this multiplied by the derivative of the second plus the second multiplied by the derivative of the first. So I just use here a sum, sorry, not sum, but a product of, or the derivative of a product. Okay, so this is simply, of course, it's still a partial derivative of a product. Partial in the sense that we only take the derivative of this product by assuming the others as constant and making the variable of consideration the position variable. So let's take a look at this derivative first here. What is drj drm? Okay, so this is a special meaning because if I take the derivative of the same variable with respect to that variable, I'm simply taking the derivative of a what? A tensorial notation in terms of an mj. So my free index in mj, so I have a second order uh, tensor. So my number of components will be 9. Okay, so I have now a dr1, dr1, okay, dr2, dr2, and dr3, dr3. So let me make it more okay. So I have the derivative of r1 with respect to r1. That's my mj11. Then I have a derivative of r2 with respect to r2. And I have a derivative of r1 with respect to r2. Derivative of r1 with respect to r3. Then the next, I have the derivative of r2 with respect to r1. Derivative of r2 with respect to r2. And derivative of r2 with respect to r3. And on the third row, I have a derivative of r3 with respect to r1. Derivative of r3 with respect to r2. And the derivative of r3 with respect to r3. Okay, so I have now here a 9 component or simply a 9 component tensor, or simply a second order tensor in the range of 3 as far as the spatial dimension is concerned. And what is the derivative of a variable with respect with the same variable? Though this is simply equal to a 1, 1, 1, and the derivative of a variable with respect to another variable is 0. Okay, so since we are talking here of partial derivatives, so these are 0, 0, 0, 0, 0. Hence, what is this? This is simply equal to the delta mj. Okay, that's why notice that here there appeared a delta mj in the simplification of this. Plus, this is a stress tensor which is not given, so we cannot simplify this further and put it at, as it is here. Okay, and then upon doing the contraction procedure on delta mj, sigma mi, I can make use of a sigma ij, okay, which is this one, plus rjd sigma mi drm. Okay, so this is now the simplest that I can get, and adding it to the body force and the body moments here. These are both the body uh, uh, expressions. Okay, so this is the force, or the body force, simply the weight, and this is the body moment. I will now yield to an expression that can can make this a two-term or a two-expression equation by simply factoring out epsilon ijk rj dv here. Okay, so this is an epsilon ijk rj dv. So I have this added to the rho fi there, this one. Okay, and take note that this term inside the second parenthesis vanishes to 0 simply because as delta v approaches 0, the body force and the derivative of the stress tensor cancels each other. And I want you consider it a proven case for the meantime. No? So let's not dig deeper into this, but just take a look at considering infinitesimal volumes in which your weight becomes very negligible. At the same time, the derivative of the stresses that will be involved, no, in a very small volume will also be very small, such that these two here cancels each other, and making the equation simply a function of this epsilon ijk sigma ij, also considering your body moments to be zero because of the infinitesimal value of your volume dv, differential volume dv. Okay, so what's the meaning now of this epsilon ijk sigma ij? If I'm going to expand this, this will only yield to a contraction, okay, such that I will be having three equations, okay, in the form. So if this contracts, take note that epsilon ijk has only values of positive and negative permutation, or simply even and odd permutation, such that the positive will be written on the left side and the negative permutation will be written at the right side. Okay, so this is the even permutation and this is the odd permutation. Or we can just write it as sigma ij minus sigma ji is simply equal to 0. So this is equivalent to this equation here, such that if I expand this, so this simply means that my sigmas, okay, my sigma upon which there is no repetition, okay, there is no repetition of subscript will involve symmetry. Okay, so we are now concluding a property of symmetry in this equation, okay, which means that this is equal to sigma 2, 1. Then a sigma 2, 3 will mean an equivalence to sigma 3, 2, and a sigma 3, 1 will mean equal to sigma 1, 3 because of this derivation. So in short class, the equilibrium equation which is defined here, okay, here in this general equation, uh, ought to prove the property of symmetry of tensors. That's why we no longer fear any miscalculation upon which your sigma ij and sigma ji will be written, no? Whether it is a transpose or an upright matrix or tensor, the values will be the same. So the inconsistency in writing a sigma ij and a sigma ji does not give you an inaccurate answer because these are just equal. But in other cases, in general, these values may be different if the symmetry property is not satisfied. Okay, so thank you very much for listening. So I hope you have gained the needed information on the equilibrium equations involved uh, in this continuous body as referred to in this presentation. I'll see you on the next video.